Hey everyone, welcome to University of Winnipeg Chemistry 1112. UChem 42U is the other code name for it. Dr. Carroll here. We're looking today at the first screencast for Chapter 12, all about spontaneity of chemical processes, entropy, free energy, enthalpy. Lots of this stuff is going to be new to you. There'll be a little bit of review from grade 12, but most of it is new. Quite theoretical, a little bit of math, interesting stuff. So this is chapter 12, and it starts on page 554. Look at this neat effect I have going on here, don't I? So we're going to look at spontaneity, entropy, which is a measure of dispersal of matter and energy, entropies of pure substances, spontaneity and free energy, a few applications of thermodynamics, and the last bit we just look at a little on bioenergetics. So this will probably be 3 or 4, maybe even 5 lectures. We'll see how we break it up. And so there's a bit of a motivational paragraph at the beginning. You can read that on your own, and let's get the business here. So spontaneity, we aren't talking about spontaneous personality here, nothing like that. We're talking about a thermodynamic specific exact term, which is the direction a system will proceed left to its own devices. So if we say a reaction is spontaneous, then we mean as written. So going from left to right, the reaction will continue without outside intervention. You might need a little push to get things going, let's say like rolling a rock down a hill. So give it a little push, then assuming no friction, it'll keep going and going and going. So that is a spontaneous process. In biology, aging, I keep getting older, right? Okay, I can do anything I want to try to fight that, color my hair and get a facelift and all this, but it's not going to prevent the fact that I'm aging. So that is a spontaneous process. Rust on your car, okay, especially in Manitoba. If you got an older car, you're going to have lots of rust because we got snow and salt and other junk all over the roads. So those are spontaneous process. Hydrogen and oxygen gas coming together to give you liquid water, that's a spontaneous process as well. Once it happens, it keeps going on. You have to spark it to give it enough activation energy to make it begin, but once it happens, it keeps going. So if it's not spontaneous, then it would be spontaneous in the opposite direction. So as you see here in the key concept, a process that is spontaneous in one direction is non-spontaneous in the opposite direction. We have here in our natural gas furnaces, methane gas plus 2O2 gas goes to CO2 gas plus 2H2O. So once your pilot light causes the spark, then you're going to burn the methane. Okay, this is not telling us how quickly a reaction happens. It's just telling you that it can happen spontaneously once it gets started. So thermodynamics and kinetics, certainly they talk to each other, but they are separate concepts, and we have to be careful about that as we go through some things. We don't go spontaneously back the other way. It says here, water and carbon dioxide do not rearrange into methane and molecular oxygen, even in the presence of a spark. It's because it's a non-spontaneous process. And we're going to learn, as we see here, CO2 and H2O are more disordered than CH4 and O2. And we tend to go in a level of disorganization, of increased entropy. You may have talked about entropy a little bit last year. Entropy is given the letter S, and it's a measure of disorder. So if delta S is positive, it's a state function. If delta S is positive, we say we are getting more disorder in the process. If delta S is negative, then we're getting more ordered. Okay? And in addition to delta S, we're also going to talk about delta H. And we're going to talk about delta G, which we're going to learn is delta H minus T delta S. So that's coming up in this chapter. Okay, so let's see here. I remember from last year, this first bit is a little bit wordy, and I want to take out some of the stuff that is just a bit too much and not necessary to go through an intro class. So, to gain some insight into why processes have preferred directions, consider some large-scale events that go in one particular direction. So a bag of marbles drops on the floor will scatter, but the marbles will not roll spontaneously back into the bag. That is true, isn't it? Okay, so that's a spontaneous process. We are dispersing matter where those marbles take up all the space they want. It's like if I have to share an office with other teachers, which I always do, it seems, or a room, the other teachers always seem to have all their stuff take over every cupboard in which my stuff is. It just naturally squeezes me into a smaller space of all my papers. Anyways, an untended wooden fence eventually falls apart, but piles of wood will not assemble spontaneously into fences. Yes, that's true, so that's spontaneous. A student's dormitory room naturally gets messy, maybe your room, but unfortunately does not spontaneously clean itself up. Okay, so there you go. They were trying to be funny there. Each of these processes has a spontaneous direction in which matter becomes more spread out or dispersed. Another way is saying that each process reduces the constraints on the object. There's more possibilities. So we can have a common sense law that things tend to become dispersed. Does it apply on a molecular level? Let's see here. We have a bulb of nitrogen dioxide, which is over here. And courtesy of Patrick Watson, whoever that is. Okay, I'm looking at the bottom of page 556 here. And second bulb is empty. Okay, so this is bulb 1. This is bulb 2. And then when the valve that connects the bulb is open, the red-brown gas expands to fill both. And you see that the intensity of the color decreases a bit. You don't, opposite process never occurs spontaneously. That is, if both bulbs contain NO2 at the same pressure, opening the valve never causes the pressure to rise in one follow the other, right? If you have the same things here, open the valve, that's not going to all of a sudden have all of it zoom into the same container. Okay, maybe they're at the same pressure. So we have a molecular view of what's going on. The direction of spontaneous change when I open the valve. So here I turn the valve, and now we see we have equal amounts in each bulb. Okay, here we have a case of sugar dissolving in coffee. That involves dispersal of molecules. So we dissolve this sugar and it spontaneously dissolves. You don't get the little crystals of sugar, individual molecules rearranging themselves back to a nice sugar cube once it is dissolved. That is not a spontaneous process. Okay, so let's see what else we have here. I'm just skimming through this. You can read through this on your own more carefully. Sugar molecules are more dispersed when they're dissolved in coffee when they're part of solid crystal, right? A sugar cube is the molecular equivalent of a tidy dorm room. Sugar molecules disperse, destroying the compact molecular organization of a sugar cube as the cube dissolves in the coffee. So, dispersal of matter is one thing. Now, another thing that happens is that energy can be dispersed. You can have, even if there isn't an obvious dispersal of matter, you still have a preferred direction for a process. Figure 12.3, we see here a hot block of metal. That looks like copper, doesn't it? Was placed in a cold glass of water. We remember this way back from chapter 3. So the metal block cools and the water warms until you get thermal equilibrium, you get the same temperature. Whenever two objects at different temperatures contact each other, the object at higher temperature transfers energy to the one at lower temperature. So this is an example of energy dispersion. That's word is hard for me to say today. Dispersal. So a higher temperature larger average thermal energy, and you want to go from higher to lower thermal energy. Thereby you are dispersing the energy. When a baseball pitcher throws a fastball, all of the molecules move through space. That's the energy constraint. Kinetic energy in the same direction. When it hits the catcher's glove, we get kinetic energy makes the glove hotter, right? An increase in temperature of the glove. And those molecules in the glove move with larger average speeds, so the molecular speeds increase in all directions. In other words, the directional character of the ball's kinetic energy is dispersed into randomly directed energies of molecules in the glove. So you can have matter transfer and or energy transfer. Can we use energy changes to predict spontaneity? Energy changes alone? The answer is no. Let's say we have the melting of ice at room temperature and the formation of ice in a freezer. So in this picture here, very exciting picture, I got a cup of water sitting on a table. The energy absorbing process, melting, is spontaneous under these conditions. Okay, so we have this ice-water mixture from the table, which is the surroundings, to the system, which is the ice-water mix. We have a energy dispersal. Okay, and that's going to help to make it spontaneous. So let's look at the picture more carefully. As diagram figure 12.5, ice melts spontaneously if a mixture of water and ice is placed on a table at 25. So you start with H2O solid. You got a tabletop at 25 to H2O liquid. Okay, well, yeah, the temperature inside will stay at 0 degrees Celsius until all the solid melts. Okay, so the water-ice system gains energy as the ice melts. The enthalpy change of the system is therefore positive. It's gaining energy. Enthalpy change will also be positive. Now, if you're at negative 15 degrees Celsius, well, then it's going to freeze. It's not going to melt. So to form the solid from the liquid, you have to remove energy to allow the molecules to hold together in the solid phase. So in this spontaneous process, the water-ice system releases energy as water solidifies, and the enthalpy of the system decreases. Okay, so both these systems are spontaneous. They do depend on the temperature, and one process is endothermic, the other is exothermic. Energy and enthalpy of the system increases in the freezing, but decrease in the melting. The simple example demonstrates that analyzing energy and enthalpy changes alone isn't enough to predict if a process is spontaneous or not. You need to look at property other than energy and enthalpy to use thermodynamics to determine if a process is spontaneous. And that is, again, where the entropy comes in. Okay, so a bit more of a build-up of this. I told you this was a bit of a wordy chapter. We have energy releasing process is spontaneous when we are freezing. Okay, when water freezes, you have more constraints. So it seems like a violation of the common sense law. But you have to look at energy changes as well. So your energy is dispersed as a result of the energy transfer. So you have freezing, constraining the matter, right? But dispersing energy. So your delta S is negative, but your delta H is positive. And so that is freezing constrains matter. So it's, you're getting entropy change negative, delta S positive. So you have opposing dispersal trends between energy and matter. Melting of ice is the reverse, and melting disperses matter but constrains energy. So there's a picture of what's going on. Okay, so this is all a build-up to defining entropy, and let's get right into it. Entropy is a measure of dispersal in the spontaneous direction of any process towards greater dispersal of matter and energy. So to talk about the quantitative measure of dispersal, we use the letter S, named after an Austrian Ludwig Boltzmann, and it is equal to a constant K times the natural log of W, which is the number of ways of describing the system. So the more ways you can describe the system, the greater the entropy. We are not going to use that equation, just qualitatively. More ways to describe the system, more energy states you can have that system in, sometimes called microstates, then the greater the entropy. It's funny, Boltzmann was an outsider in the, I don't know if it's funny, but it's interesting, an outsider in the scientific community, in the old boys club, as they said. And he came up with this idea about entropy, and most people said, no, you don't know what you're talking about. So Boltzmann had it arranged so that on his tombstone would read that equation, S equals K natural log of W. So indeed, his tombstone does say that, and he was proven to be right, but he was already dead, so there you go. Anyways, he wanted sort of like a take that scientific community. So I'm not going to get into all the probability about that. This equation comes in a little earlier than I would have put it, equation 12.2. An energy transfer results in either dispersal or constraint of energy and just generates a change in entropy. When a flow of heat occurs at constant temperature, equation 12.2 provides a quantitative measure of the entropy change. So the entropy change is the heat flow at a constant temperature over the temperature at what that process happens. If we're talking about a phase change or transition, delta S transition equals the transition heat, could be like delta H of fusion or delta H of condensation, let's say, over the temperature at which that transition happens. So entropy changes are given in units of joules per Kelvin or kilojoules per Kelvin, and later we're going to see that it can be for a certain amount, a certain number of moles of reactants or products, and it could be joules per Kelvin per mole. So to put this in words, when heat flows at a constant temperature, the entropy change is equal to the heat transfer divided by the temperature in units of Kelvin. Always Kelvin. Okay? This is always restricted to processes that occur at constant temperature. Heat flow changes dispersal of energy. The amount of change depends on the magnitude of the heat flow. Okay. And changing the temperature changes dispersals of heat. Important change types of chemical processes occur in which heat flow takes place without a temperature change. Phase changes, will they take place without a temperature change? Absorbing or releasing heat in the process. Chemical reaction may occur under conditions in which temperature is held constant, such as in the human body, right? 37 degrees Celsius, or a thermostated automobile engine. Okay, even though the temperature stays constant, exothermicity or endothermicity generates the heat flow. And the surroundings may be so large they can absorb or release significant amounts of heat before temperature changes by a measurable amount. Okay, so if you're in a constant temperature water bath, that's an example of keeping the temperature constant. So let's look at an example here about how all this works with some numbers, shall we? So this is on page 561. We want to find out what's the total entropy change when 2 moles of water freezes at 0 degrees Celsius in a freezer compartment in which the temperature is held at minus 15 degrees Celsius. Okay, so you got a cup of water, glass of water, 2 moles, and you're going to have it put into a freezer where the temperature is minus 15 degrees Celsius. Okay, delta H fusion is 6.01 kilojoules per mole at 0 degrees Celsius. So that is the energy, well, if it's freezing, so put a negative sign in front of that, and that would be the energy released per mole at 0 degree. Now the total entropy change includes the water and the freezer compartment, right? Both those objects have a change in entropy. When water freezes, heat flows from the water to its surrounding, the freezer compartment. So Q is negative for the water, right? Go back to chapter 3. We are releasing energy into the surroundings, and also the system is becoming more ordered, right? It's going to a solid. At the same time, Q is positive for the freezer compartment, and its entropy increases. Okay, so that is the strategy. So we need a way to determine Q, and we must identify T for the water and for the freezer compartment because they're different. The water-ice mixture remains at a constant temperature while the phase change occurs. I mean, once it's all ice, yeah, then it'll cool to minus 15. But once you're going, but before that happens, you are having a two-phase system there, right? At equilibrium at 0 degrees Celsius, the liquid water and the ice. The question asks only about the freezing process. It doesn't ask about the cooling down to minus 15. Okay, so the freezer's at a constant temperature of minus 15 Celsius or 258 Kelvin. The ice-water mixture is at a temperature of 0 degrees Celsius or 273 Kelvin. We have 2 moles of water and we got the heat of fusion. So, to calculate Q for the phase change, Q is N times delta H of fusion, right? 2 moles times 6.01 by 10 to the 3 joules per mole. And the entropy change for the constant temperature presence is delta S is Q at that constant temperature over constant temperature process over the temperature. Okay, make sure it's in Kelvin. So Q for the water is negative 2 moles times 6.01 by 10 to the 3 joules per mole. So you get negative 1.02 by 10 to the 4 joules. And delta S then of the water is that QH2O over the temperature at which the freezing happens, 0 Celsius, 273.15 Kelvin. So the delta S for the H2O is negative 44 joules per Kelvin. So you're getting more ordered, right? You're going from a liquid to a gas. We're going to talk more about the properties of water in oh no, you've already talked about it, haven't you? We talked about that in chapter 8, right? And hydrogen bonding and all that. But the delta S is minus 44. The freezer compartment absorbs the heat released, but it absorbs it at its temperature. It wasn't at 0, it was at minus 15. So the Q of the freezer is opposite to the Q of H2O. So it's 1.202, positive 1.202 by 10 to the 4 joules. And the delta S of the freezer is that value divided by the temperature of the freezer, 258. So it's 46.6 joules per Kelvin. So the total entropy change is the water plus the freezer. It's going to be slightly positive, right? So that means that this is a spontaneous process. 2.6 joules per Kelvin. So you take the delta S of the H2O and the delta S of the freezer, and you get 2.6 joules per Kelvin. Now with all this qualitative stuff, it's very useful to read the section where it says, does the result make sense? Here we go. The negative sign for the entropy change of the ice-water mixture is consistent with our qualitative view that matter is more dispersed in a liquid than in a solid. Okay? The positive sign for the entropy change of the freezer is consistent with heat being absorbed by the freezer, which increases the dispersal of energy. Delta S total is greater than 0, which must be the case for a spontaneous process. Now, you might say, why must? We haven't even talked about that. System and surroundings together gives you the universe. If delta S total is greater than 0, you know it has to be a spontaneous process, because that, fellow chemists, is the second law of thermodynamics. First law is there's no fight club. The second law of thermodynamics, no, the first law is conservation of energy. The second law of thermodynamics says that the entropy change of the universe is greater than 0 if you're looking at spontaneous processes, which is what's happening here. Okay? Let's try this example here. I need my calculator for this one. We want to find stuff about a tea kettle. Enthalpy of vaporization of water is 40.79 kilojoules per mole at a normal boiling point, right? That's TB, normal boiling point, 1 atmosphere, 100 Celsius, so we know that's 373 Kelvin. Calculate the entropy change for water and for the hot plate, and the overall entropy change when a tea kettle on a hot plate at 250 Celsius, what is that, 423 Kelvin, boils off 3.55 moles of water. Okay, so for the water vaporizing, the Q is going to be going from a liquid to a solid, so we're pouring energy in. It does boil at 100, so we got to look at that. That's where we're getting the vaporization associated with 100. So Q is going to be 3.55 moles times 40.79. Now, is this joules or kilojoules? So this is kilojoules. Okay, so 3.55 times 40.79 equals 144.8. So that is going to be kilojoules. And now the delta S associated with that process is going to be Q over T. So 144.80 kilojoules over a temperature of 373 Kelvin. And you get 0.388 kilojoules per Kelvin. Okay, so that is associated with the vaporization process. Okay, and things are getting more disordered. You're going from a liquid to a gas, so that's okay. Now we got the hot plate. So how are we going to do that? We are transferring Q from the hot plate to the water. So we're transferring 144.8. So delta S of the hot plate will be minus 144.80 kilojoules over the temperature at which the hot plate's at, 423. So 144.8 negative divided by 423 is minus 0.342 kilojoules per Kelvin. So then my total delta S, you add those together, minus 0.342 plus 0.388, and you get 0.04 delta S water minus 3, oh, that's in joules, okay. Minus 277, let's see, 144, 250 plus 273, 523 Kelvin. Some of you were saying, why did he write 423? It's 523. 523 Kelvin here. Okay, so 144.8 negative divided by 523 is negative 0.277 kilojoules per Kelvin. So now add those together. 0.388 minus 0.277, and you get 0.111 kilojoules per Kelvin. And I see the answer key gives it in joules per Kelvin, so you multiply by 1,000, 111 kilojoules per Kelvin. So this is a spontaneous process. You will form steam when you boil water on a hot plate. Now you know. There's the numbers. Okay. Then we just had to talk about the negative values. For any spontaneous process, I already said this, but here it is again. The total change of entropy is a positive quantity. Thus, this new state function of entropy provides a thermodynamic criterion for spontaneity, which is summarized in the second law. In any spontaneous process, the total entropy increases. So here we have figure 12.10. Well, it's just a picture again. I'm not going to repeat it. Signs associated with heat transferred: exothermic system negative, surroundings positive, water freezing, endothermic, the other way around. Then pictures showing the story. So the total entropy is delta S system plus delta S surroundings. And you can try example 12.2 on your own. It's the same kind of story that we just looked at. So I'm not going to look at this one again. Okay. That part's not that helpful. And so let's look at one more topic here today. Let's look at the entropies of pure substances. And I'm going to jump straight down to, since I mentioned the second law of thermodynamics, let's talk about the third law of thermodynamics, which says if you have a pure perfect crystal, the entropy of that pure perfect crystal is 0 at a temperature of 0 Kelvin. Okay, so entropy is an interesting thermodynamic function in that it does have an absolute value of 0. Enthalpy, you're really looking at differences, delta H. You don't talk so much as an absolute 0 value for enthalpy. But with entropy you can, so you can talk about S. And it has to be a perfect crystal. So what do we mean by that? Let's say we take carbon monoxide and take it down to absolute 0. So take a snapshot of it. So you may have this like repeating pattern, CO, 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 and then back again. So it might be nice, perfectly ordered. And at 0 Kelvin, we're saying its disorder is 0, so its entropy is 0. But if I change one of these, even just one, have it flipped around, now we got a bit of an imperfection in there, right? It's an impurity. It's not perfect anymore, and now the entropy would be slightly more than 0. So if a sample is not a perfect crystal, the imperfections can have multiple locations. This can happen in all sorts of different places, and so the entropy will be greater than 0. And someone said, well, doesn't everything stop at 0? No, it doesn't. You still have vibrations around what are called the lattice points. We talked about lattices before, didn't we, in chapter 8, when we were looking at solids. So this, by the way, is on page 566. So this is the third law of thermodynamics, and it allows us to talk about absolute entropies of any system As you increase the temperature, you increase the temperature. That's an important point. I'm going to put a star there. So there's a figure talking with argon. So let's look at that here. Where's that picture? Okay, so we have argon at 0 Kelvin. We heat it. And if you heat it, so now they're vibrating, the argon atoms are vibrating more quickly. At 83 Kelvin, now the solid starts to melt. Notice that the temperature stays constant. And so now we're taking up more room as we form a liquid. We keep heating the liquid, the entropy goes up. Then the temperature stays constant as we vaporize it. And the entropy goes up again. So the entropy increases as the temperature increases when a solid melts and when a liquid vaporizes. You can probably guess, or even looking at this picture, you see that the greatest increase in entropy is the phase change here from liquid to gas, because you're really going into a huge region now of possible microstates of energy. So you get entropy increases for both the phase changes and for also just ramping up the temperature. When I say ramping up, that means I'm increasing the temperature. Okay, so when the solid melts at 83.8, we have an entropy increase. Okay, we got 1 mole of argon, and you would be given the delta H of fusion of argon, so 1.21 by 10 to the 3 joules happening at the fusion temperature, the melting temperature, so it's 14.4. So you get an increase from going from solid to liquid, then going from 83 Kelvin to 87.3 Kelvin. That's got to be, yeah, that's good. Sorry, I started to think about negative Kelvin. I said, wait a second, there's no such thing as negative Kelvin. It's positive Kelvin. So you get additional increase in entropy as the argon atoms gain thermal energy. Then when the argon vaporizes, there's another big increase. And look at that, 74.8. So the vaporization of the dog's running under the table. My goodness, go away, dog. I'm doing entropy stuff. I'll talk to you later. Okay, yeah, the dog's run away. So 6.53 kilojoules per mole is the vaporization, and then you divide that by the temperature at which it vaporizes, and you see you get a greater increase in entropy when you go from a liquid to a gas than a solid to a liquid. So now when we go, now we see the chart there, and we can hear you, dog. Okay. You can look at any starting point. You can choose any gas you want and go through this, solid to liquid to gas. So the third law establishes a starting point for entropy. At 0 Kelvin, any pure perfect crystal is completely constrained at 0 joules per Kelvin. Higher temperature, you get larger values. Okay, and molar entropies for many pure substances have been measured at 1 bar and 298 Kelvin, standard condition. And they're the same, they can be put in the same tables as your delta H naught values. Now, these values are called S naught. Okay, it's not snot. Kids always laugh and say, "Oh, he's talking about snot." It's not. It's not snot. It's S naught. Okay, stop with the silly joke. So S, it's a little 0 there. In Britain, they call that a naught. And so you have an example here of some standard molar entropies of selected substances at room temperature and 1 bar, and you see that there's more disorder in something like ethane, C2H6, then ethene, then ethine, then methane. It's got more disorder, there's more molecules, more atoms in a molecule, different kinds of vibrations and rotations, different states of energy, microstates, so you get a higher entropy. All things being equal, here we have noble gases. The more electrons there are, the greater the molar mass, the greater the standard molar entropy, joules per mole per Kelvin. Graphite is slightly more disordered than diamond. They're both carbon. They're allotropes, right? You remember that word, allotropes, A-L-L-O-T-R-O-P-E-S. But the graphite allows more sliding of the atoms over each other, so there's more disorder in the graphite than in the carbon. And you can make other comparisons. So this is a nice chart of some standard molar entropies. You can read about absolute zero on your own there. And an important feature not revealed in that table is that binding atoms into molecules always constrains the atoms and reduces the total entropy. Right, if you form a molecule, you'll get less entropy before. There's other things that happen, but sample containing 2 moles of helium has more entropy than 1 mole of hydrogen, even though both samples contain the same total number of atoms. So if you've got more moles of gas, you are going to have more disorder. Okay. What are some more stuff about this table? S0 values are never zero at any temperature above Kelvin. They're always positive. Absolute entropies can be zero only at 0 Kelvin. But can the S0 values be negative above zero? I don't think so. I don't think that makes any sense. No, it doesn't make any sense, so it stays positive. Absolute entropy depends on its phase. So we have here 3 substances. They're quite similar. Well, there's more fluorine, chlorine, bromine. There's more electrons in iodine. So if they were all in the same phase, iodine would have the greatest disorder, the greatest S0 value. But here we have different phases, so we see that again, the gas dominates, even though there's less electrons in chlorine than bromine or iodine. Look at that though. The phase change is crucial. It overrides the number of electrons. So chlorine has a higher S0 value than bromine. Chlorine gas has a higher S0 value than bromine liquid, has a higher S0 value than iodine solid. The more constrained phase, the solid is the most constrained, has the lower entropy. Similar, so S0 solid is S0 less than S0 liquid is less than S0 of a gas. If you have the same phase and similar structure, then you have increase in molar mass, causing an increase of S0. So argon and helium are both gas. You see that S0 for argon is more than S0 for helium. Silver and copper are both solids. Silver's got a greater molar mass, so it's got a greater entropy. Okay. As I said earlier, the more complicated a atom arrangement to create a molecule is, the greater the standard molar entropy. So we see there's my ethane, C2H6. It's got a greater molar entropy than C2H4, which is a greater one than C2H2, because there's just more vibrations, more rotations, more things can happen, more ways to distribute energy, and therefore greater energy dispersal, greater entropy. Let's look at this example here. Where I have 1 mole each of Hg and Au. Which one would have the larger entropy? Well, it's the one with the greater molar mass, assuming they're both solids, but they aren't. Mercury is a liquid, gold's a solid, so I'm going with mercury as the winner. Let's see what the molar mass. Mercury has they have almost the same molar mass. Okay, so liquid mercury should have a larger S0 value, and that's true. 76 versus 47. So molar masses are similar to each other. What are they exactly? I'd rather say number of electrons, but the book wants to talk about molar masses. Go ahead. Mercury's molar mass is 200, and what was the other one there? Gold? What are we comparing? Mercury to gold, 197. So they're really close to each other. So the fact that mercury is a liquid means it's going to have a larger standard entropy. Then we got NO and NO2. Well, if they're both gases, NO2 has a larger molar mass and it has another bond going there. So it's more complicated. So it's going to have a greater standard molar entropy, 240 versus 211. 2 moles of NO2 versus 1 mole of N2O4. Now that's a tricky one because the molar masses, when you add them together, are going to be the same. But you got more moles of NO2 than N2O4. So I think I'm not looking at the answer yet. I think that arrangement will have a greater standard entropy. Let's see. 2 moles of NO2 should have more entropy than 1 mole. We got 480. 2 moles of 240 joules per mole versus 304. So, if it was just 1 mole of NO2, then the N2O4 would win because it's more complicated. But 2 moles, you get 480 versus 304. Okay, that was a little tricky. 1 mole each of xenon and krypton. Xenon has a higher molar mass, so it should have greater entropy, 170 versus 164. Okay. Let's look quickly here at practice exercise 12.3. For each of the following pairs, select the one with the smaller S0 value. CH4 or SiH4. Well, they're both gases, so CH4 has a smaller molar mass, so it will have a smaller S0 value. B is CH4 gas or H2 gas. Well, H2 gas is going to have a smaller S0 value because there's less atoms and the molar mass is smaller. CH4 gas or H2O liquid. Here we got different phases. We got roughly the same molar masses, 18, 16, so that's pretty close. So it's the phase change that is going to dominate everything here, determine things. So H2O liquid, because it is a liquid, will have a smaller S0 value. Okay, so these are some qualitative with a pinch of quantitative stuff that you have to be able to determine. Let's finish off this section 12.3. I was going to break it into 2 parts, but let's just finish it off. It's easier to keep things arranged that way, I think. We were fighting disorganization. Entropy increases, as we said, as the substance spreads out. The molar entropy of a gas is larger than the molar entropy of the same substance, liquid or solid. We said that before. Molecules are more dispersed in a gas phase than in a condensed phase. And the dogs are getting a bit disorganized as well. There's similar increases in dispersion if a solution is diluted. Okay, if you have more solvent, then there's more places for the solutes to go, and that's what dilution does. So diluting something is going to change the entropy of the system. Dilution of a solution has the same dispersion as expanding a gas into a larger volume. So if I decrease the concentration of my solute, and I'm looking at that, then the entropy of that solute is going to increase if the concentration decreases. Okay, there's more places to go. I'm not piled up as much. So I see here's a gas expanding, there's more places to go. Solution is diluted. Well, these little circles now have more places to sample, so their entropy increases as the solution is decreased. When a solution is diluted by a factor of 2, the increase in dispersion is the same as when the pressure is reduced by a factor of 2. Okay, so you're trying to make some comparisons here. It can be shown, when they don't want to go through all the math, they say, it can be shown that at a non-standard concentration, the entropy S is S0, so at the standard concentration minus R, there's a gas constant which seems to pop in everywhere, natural log of C, the concentration C over C0. So If you are at standard concentrations, then this term will all vanish and S will equal S naught. And remember PV equals nRT, so we can, instead of C, we can do a ratio of pressure if we're talking about gases. C over C naught is P over P naught, and you can say, we know that the standard concentration is 1 molar, the standard pressure was 1 bar, so we can just write it as the entropy with regards to a gas at any non-standard pressure is the entropy at that standard pressure minus the gas constant times the natural log of the pressure that you're at in units of bar. And if the concentration is not 1 molar, then the entropy is S naught minus R times the natural log of C. And you're given these equations, you don't have to memorize it. So bar for gas and molarity for solutes. So let us calculate that. So oxygen has many applications for welders, from welders' torches to respirators. The gas is sold commercially in pressurized steel tanks. One such tank contains oxygen at 6.5 bar and 298 Kelvin. Using standard thermodynamic data, compute the molar entropy of the gas in the tank at 6.5 bar and the change in entropy of a 0.155 mole sample of gas withdrawn from the tank at 1.1 bar and constant temperature. Okay, so we want to find two things. The molar entropy in the pressurized tank, 6.5 bar, and the change in the entropy when you take some out at a different pressure. So let's start with the first thing. Begin with a diagram of the process to include a summary of all the information we need. We need the absolute entropy of O2, which is 205 joules per mole per Kelvin. That is at 298 Kelvin. Okay, so here we go. We have a tank of oxygen gas, pressure of 6.5 bar, temperature 298 Kelvin. We're going to remove some gas and see what happens. The gas stored in the tank is not at standard pressure, so let's apply equation 12.5 to calculate its molar entropy. So 6.5 bar, S naught, we got that 205 minus R, 8.314 joules per mole per Kelvin. Okay, times the natural log of 6.5. I'll let you make sure all the units work out. And you get a value of 189 joules per mole per Kelvin. So you see that the S value is not the same as what you started. It's only 189 now. Now, when you're looking at the oxygen at 1.1 bar, the S value is 204 joules per mole per Kelvin. So delta S is the final minus the initial, 204 minus 189. So it's 2.3 because I had to multiply by how many moles I was taking out. I was taking out how many moles was that? 0.155. So we see that we did get a positive entropy change. The positive value reflects the fact that the expansion is a spontaneous process, right? If you just open the valve, you aren't going to get a bunch of oxygen being sucked into the tank, right? You're going to get oxygen taken out of the tank. Hey, it actually makes sense, right? Inside the tank, we were more pressurized than outside. Outside, we're basically This is basically just an everyday room here, right? 1 bar, 1.1 bar, not a huge difference. But pressurized tank, 6.5 bar, so my delta S is positive. It is a spontaneous process. I'm getting disorder just by opening the valve in the gas tank. Here we want to get the entropy change. Shall we try practice exercise 12? Or why not? 125 grams of helium. Well, helium is 4 grams per mole. So let's get the moles right away. 125 divided by 4, 31.25. So 31.25 moles of helium. My pen's too thick. Let's get it real. There we go. 31.25 moles of helium. Initially at 298 and 1 bar is compressed to a new pressure. Okay, so the initial one, S, at 298 and 1 bar for helium is going to be, well, now that was in that table. I don't have to go to Appendix D. I think it was in the standard molar entropy. I got helium there. 291 bar, it's 126.153. Joules per degree Kelvin per bar. So that's my S naught for helium. Now it's compressed to a new pressure. So S naught at 15.7. Now what's that equation again? You'll be given it. S is S naught. Okay, it's not S naught, just S. Can't be S naught. S naught is only for 1 bar. How many times can I say S naught? S at 15.7 is S naught, 126.153 minus R, 8.314 times the natural log of 15.7. So I get 126.153 minus 8.314 times 15.7 natural log, and I get 103.26. So the entropy change then, delta S, is the moles, 31.25 times 103.26 minus 126.153. 103.26 minus 126.153 times 31.25 minus 715 joules per Kelvin. And that's what the back of the book says. Hooray. Okay, one last topic here. How am I doing for time here? This might be one of the longer ones, but hey, that makes it more fun, right? Okay. Entropy changes are important in every process, but chemists are particularly interested in the effects of entropy in chemical reactions. If a reaction occurs under standard conditions, its entropy change can be calculated from the absolute entropies using the same reasonings used to calculate reaction enthalpies like we did in Chapter 3. The products have molar entropy, so do the reactants. The total entropy of the products is the sum of the molar entropy of the products multiplied by their stoichiometric coefficients minus the reactant. So this is something you have seen before with delta H. We can use this Greek letter nu to represent molar coefficients. I sometimes like to use n, but I'll use what they want. So delta S naught of reaction is the sum molar coefficient of each product times its S naught value minus the molar coefficient of each reactant times its S naught value. This looks very similar to Chapter 3, right, where we had delta H naught of the reaction is the sum of the molar coefficients of each product times its delta H naught of formation value minus the reactants. Okay, so here's a reaction: acrylonitrile makes fibers, great, all that. Calculate delta H naught and delta S naught for the synthesis of acrylonitrile. So I guess I need, what's my chemical reaction? There it is, 2C3H6. I'm going to rewrite it here. 2C3H6. The products are liquids, the reactants are gases. 2C3H6 plus 2NH3. Plus 3O2 goes to form. Oh, I put in an equilibrium symbol there. How about that? We'll get to that. I'll just make it fine. 2C3H3N plus 6H2O. Okay, and then from Appendix D, which I'm going to photocopy and give you each a copy so it's easier for you to reference it, we see all these values for them all. Notice O2 has 0 for delta H naught F, but its S naught is not 0, okay? We aren't at absolute 0, so that's the difference between delta H and S naught. Also, notice that this is a biggie. Delta H naught F in the appendix is listed in kilojoules per mole. S naught is listed in joules per mole per Kelvin. Okay, so we have that data. I like to convert everything into joules and then at the end get to kilojoules. The book does it. Does they do it that way? Well, oh, we don't have to do the delta H and the delta S combined together yet. When we get to delta G, then we'll have to do that. So the delta H, so you're going to take 2 times the C3H3N, so 2 times 172.9 plus 6 times the liquid water minus 285, all minus 2 times the C3H6, which is 20, plus 2 times the minus 45.9 plus 3 times 0. So this is an exothermic process with a delta H naught of minus 1317 kilojoules per mole. For the delta S naught, well, we're going to take 2 times 188. Where the heck am I getting 188 from? C3H3N. Oh, because I looked at the wrong row. There it is. 2 times 188 plus 6 times 69.95 minus 2 times 226.9 plus 2 times 192.8 plus 3 times 205.15. Remember, oxygen isn't 0 for the S naught. So you add all those reactions together, subtract them from the products, and you see you get negative 659. So that makes sense because we're forming liquids from gases, so we are losing entropy because gases have much more entropy than liquids. So according to these values, the reaction is exothermic, fine, but the products are less dispersed than the reactants. Because the reaction produces liquids from these gases, this decrease in dispersion is a reasonable result. Okay, so that is using the standard entropy, absolute entropy values. And you can try the practice exercise on your own as well as the, well, I'll quickly do splits. The last one here, what does it say about qualitatively? You do the quantitative, but qualitatively I would look at here and I'd say I got 12, I got lots of gas here, 33, just 12 here. So my guess is my delta S is going to be negative because I have a lot less gas mole coefficients on the right hand side than the less. Okay, so that was a good, fun lecture. Now you go over it all and practice everything again.